What if I told you that light, the fastest thing in the universe, is actually so pathetically slow that it makes a snail look like a speed demon? Right now, there's light that left distant galaxies when dinosaurs ruled Earth, and it's still crawling through space trying to reach us. Today, we will discover why the speed of light is embarrassingly slow. If you're ready to have your mind blown by this cosmic perspective, make sure to subscribe to this channel and give this video a thumbs up. And one quick question: if you could send a message to every intelligent civilization in our galaxy, what would you ask them? Drop your answer in the comments below. I always pin the most creative answer. Now let's begin. The light from our sun takes 8 minutes and 20 seconds to reach Earth. That seems quick until you consider that our sun is practically sitting in our cosmic backyard. The nearest star beyond our solar system, Proxima Centauri, is so far away that light takes 4 years and 4 months to make the journey. 4 years for the fastest thing in the universe to travel to our closest stellar neighbor. But that's just the beginning of light's cosmic humiliation. The center of our own galaxy, the Milky Way, lies 26,000 light-years away. This means that the light reaching your eyes right now from the galactic core began its journey when humans were still painting on cave walls. The photons hitting your retina are older than recorded human history, and they've been traveling at the maximum possible speed the entire time. Let's zoom out further and watch light's speed become even more pathetically inadequate. The Andromeda Galaxy, our nearest major galactic neighbor, sits 2.5 million light-years away. The light you see from Andromeda tonight started its journey when our earliest human ancestors were just learning to use stone tools. Those photons have been racing through space at light speed for longer than our species has existed, and they're just now arriving at your eyes. The observable universe stretches roughly 46 billion light-years in every direction. This means that the most distant objects we can see are so far away that their light has been traveling toward us since shortly after the Big Bang itself. Even at light speed, the fastest possible velocity in our universe, it takes longer than the age of the cosmos to cross the observable universe. Light isn't fast. The universe is just unimaginably, incomprehensibly vast. Here's where the cosmic perspective becomes truly humbling. We are made of stardust, literally forged in the nuclear furnaces of ancient stars that lived and died billions of years before our sun was born. The carbon in your body, the oxygen you breathe, the calcium in your bones, all of it was created in stellar cores and scattered across the galaxy by supernovae. But here's the kicker: the light from those ancient stellar explosions is still traveling through space, carrying the news of their deaths to distant corners of the universe. Consider the Hubble Space Telescope's deep-field images, which peer back in time to show us galaxies as they existed over 13 billion years ago. We're not just looking across space, we're looking back through time itself. The light from those primordial galaxies has been traveling toward us for most of the universe's history, and it's only just now reaching our telescopes. At light speed, information about the early universe takes longer to arrive than it took for galaxies, stars, and planets to form. The James Webb Space Telescope has pushed this temporal voyeurism even further, capturing images of galaxies that formed when the universe was only a few 100 million years old. These ancient light signals have been stretched and redshifted by cosmic expansion, arriving as infrared radiation after their billion-year journey through expanding space. Even light, the universe's ultimate messenger, struggles to keep up with the story of cosmic evolution. Now let's talk about what happens when we try to use light speed for practical cosmic travel. The Voyager 1 spacecraft, launched in 1977, is currently humanity's most distant ambassador, traveling at about 17 kilometers per second. At this blazing speed, fast enough to circle Earth in just over an hour, Voyager 1 would still need over 73,000 years to reach Proxima Centauri, and Voyager is already moving faster than any crewed spacecraft has ever traveled. Even if we could somehow accelerate a spacecraft 10% of light speed, a technological achievement that would require revolutionary breakthroughs in propulsion physics, the journey to Proxima Centauri would still take over 40 years. That's an entire human lifetime spent traveling to our nearest stellar neighbor. To reach the center of our galaxy would require 260,000 years. To visit Andromeda would take 25 million years. Light speed isn't a solution to cosmic distances, it's barely a starting point. The cosmic microwave background radiation, the afterglow of the Big Bang itself, has been traveling through space for 13.8 billion years. This ancient light has crossed the entire observable universe, and it's only just now reaching our radio telescopes as faint whispers of the universe's birth cry. Even the universe's own baby pictures take longer to develop and deliver than human civilization has existed. Here's a mind-bending thought experiment that illustrates light's cosmic sluggishness. Imagine you could somehow travel at light speed, the absolute maximum velocity allowed by physics. You decide to take a grand tour of the local group, our cluster of galaxies. Just visiting our nearest major neighbors would take over 5 million years of travel time. You'd return to find that Earth had experienced 5 million years of evolution, climate change, and potentially the rise and fall of countless civilizations. Light speed doesn't make you fast, it makes you a time traveler. The scale problem becomes even more absurd when we consider galaxy clusters and superclusters. The Virgo cluster, containing over 1,300 galaxies, lies 54 million light-years away. The light we see from Virgo tonight began its journey when dinosaurs still ruled the Earth. The Coma cluster sits 320 million light-years distant. Its light started traveling toward us before complex life had even emerged from the oceans. The Sloan Digital Sky Survey has mapped over 3 million galaxies across a significant portion of the observable universe, creating the most comprehensive three-dimensional map of cosmic structure ever assembled. But here's the mind-bending reality. This map doesn't show us the universe as it is, but as it was across billions of years of cosmic history. Nearby galaxies appear as they were millions of years ago, while the most distant objects show us the universe when it was just a fraction of its current age. We're not looking at a snapshot of the cosmos, we're seeing a time-lapse movie played in reverse, with light speed as the cosmic projectionist determining when each frame arrives. The Large Magellanic Cloud, a satellite galaxy of the Milky Way, sits 160,000 light-years away. This means the light we see from it tonight began its journey when modern humans were just beginning to migrate out of Africa. The stars we observe in the LMC might have already exploded, new stars might have formed, entire stellar populations might have evolved and died, but we won't know about any of these changes for thousands of generations. Light speed doesn't just limit our travel options, it imprisons us in cosmic ignorance. Consider the mind-boggling scale of galaxy collisions, cosmic events so vast they make light speed look like a snail's pace. The Milky Way and Andromeda galaxies are currently approaching each other at about 250,000 miles per hour. Sounds fast until you realize they won't collide for another 4.5 billion years. Even at this tremendous velocity, the distances involved are so enormous that the collision unfolds in cosmic slow motion. Light can cross the space between these galaxies in 2.5 million years, but the actual gravitational dance takes billions of years to complete. The cosmic web's filamentary structure reveals patterns that stretch across hundreds of millions of light years. These vast networks of dark matter and galaxies form the largest structures in the universe, but their evolution happens on timescales that dwarf human comprehension. A single vibration or wave propagating through these cosmic filaments would take hundreds of millions of years to travel from one end to the other, even at light speed. The universe operates on scales where light itself becomes a sluggish messenger. Quasars, the blazing hearts of ancient galaxies powered by supermassive black holes, can outshine entire galaxies containing hundreds of billions of stars. The most distant quasars we observe existed when the universe was less than 1 billion years old, appearing to us as they were over 12 billion years ago. These cosmic lighthouses have been beaming energy across the universe for most of cosmic history, but their light is only just now reaching our telescopes. By the time we see a quasar, it might have already consumed all available matter and gone dark billions of years ago. The concept of cosmic horizons becomes even more frustrating when we consider that the universe beyond our observable bubble might be infinite. If space extends forever in all directions, then there are infinite galaxies, infinite stars, infinite worlds that we will never see because their light hasn't had time to reach us. Light speed doesn't just limit our view of the universe, it creates an information horizon that might hide infinite wonders forever beyond our reach. Supernovae, the explosive deaths of massive stars, can briefly outshine entire galaxies and be seen from billions of light years away. But here's the cosmic irony. By the time we detect a supernova, the star that exploded has been dead for longer than complex life has existed on Earth. We're witnessing stellar death certificates that were written in the cosmic past, delivered by light that has been traveling through space for eons. The universe is full of ghosts, and light speed ensures we're always seeing the after-images of events that happened in the deep past. The cosmic microwave background radiation provides our oldest view of the universe, showing us the cosmos when it was only 380,000 years old. This ancient light has been traveling for 13.8 billion years, stretched and redshifted by cosmic expansion until it appears as faint radio waves. But even this primordial radiation represents just a tiny fraction of the universe's history. The first 380,000 years, when the cosmos was opaque to light, remain forever hidden from our view. Dark matter, which outweighs ordinary matter by a ratio of 5:1, interacts primarily through gravity and moves at speeds far below light speed. The dark matter halos surrounding galaxies extend for hundreds of thousands of light years, but changes in these structures propagate at the speed of gravitational waves, which is light speed. This means that even the invisible scaffolding of the universe is limited by the same cosmic speed limit that constrains everything else. The search for gravitational waves has opened a new window on the universe, allowing us to detect cosmic events that produce no light at all. But gravitational waves travel at exactly light speed, meaning they face the same temporal limitations as electromagnetic radiation. When LIGO detected waves from neutron stars colliding 130 million light-years away, we were experiencing an event that happened when dinosaurs still roamed the Earth. The universe's most exotic phenomena are still constrained by the same frustratingly slow speed limit. Galaxy clusters, the largest gravitationally bound structures in the universe, can contain thousands of galaxies spread across millions of light-years. The hot gas between galaxies in these clusters glows with X-ray radiation, creating some of the most spectacular images in astronomy. But coordinating the motion of thousands of galaxies across such vast distances requires gravitational signals that travel at light speed. Changes in a cluster structure take millions of years to propagate throughout the system, making these cosmic cities incredibly slow to respond to external influences. The concept of cosmic time becomes meaningless when we consider light speed delays. There is no universal clock that ticks simultaneously throughout the cosmos. Instead, We live in a universe where now depends entirely on your location and the distance to the events you're observing. The explosion of a star in Andromeda that happens now from our perspective actually occurred 2.5 million years ago. The universe doesn't have a present tense, only a collection of past events arriving at different times. Cosmic rays, high-energy particles that bombard Earth from deep space, travel at nearly light speed, but still take years or decades to reach us from their sources in distant galaxies. These subatomic messengers carry information about the most extreme environments in the universe: supernova remnants, black hole jets, and galactic nuclei. But by the time they arrive at Earth, the cosmic accelerators that created them might have already shut down or moved to completely different locations. The James Webb Space Telescope can peer back to when the first stars and galaxies were forming, just a few 100 million years after the Big Bang. But even this incredible time machine is limited by light speed. It can only show us how these primordial objects appeared billions of years ago. Their current state, if they even still exist, remains completely unknown. We're cosmic archaeologists forever studying ancient artifacts while the living universe evolves beyond our view. Pulsars, rapidly spinning neutron stars that emit beams of radiation like cosmic lighthouses, provide some of the most precise clocks in the universe. But even these stellar timekeepers are subject to light speed delays. The pulses we detect from distant pulsars left their sources years or decades ago, meaning we're always seeing these cosmic clocks running in the past. The universe's most accurate timepieces can't even tell us the current time. The expansion of the universe itself creates an additional layer of cosmic frustration. Not only does light take billions of years to cross cosmic distances, but space itself is stretching during the journey, making the effective distances even larger. Light from the most distant galaxies has been traveling for over 13 billion years, but those galaxies are now over 46 billion light-years away due to cosmic expansion. The universe is literally outrunning its own light. The Hubble constant, which measures the rate of cosmic expansion, reveals that galaxies are moving away from us at velocities proportional to their distance. At about 14 billion light-years away, galaxies are receding at light speed itself. Beyond this distance, galaxies are moving away faster than light, not through space, but because space itself is expanding between us. This creates a cosmic horizon beyond which galaxies are forever unreachable, no matter how long we wait or how fast we travel. Light speed isn't just slow, it's being outpaced by the expansion of space itself. The concept of look-back time illustrates just how trapped we are in cosmic history. When we observe the Andromeda Galaxy, we're seeing it as it existed 2.5 million years ago, before humans had developed agriculture, writing, or civilization. The light carrying this ancient image has been racing toward us at the maximum possible speed for longer than our species has been recognizably human. Even at light speed, information about our nearest galactic neighbor is older than human culture. Stellar evolution happens on timescales that make light speed delays even more problematic. A massive star might live for only 10 million years before exploding as a supernova, but if that star is 50 million light-years away, we won't see the explosion until 40 million years after it happens. By the time the light reaches us, the stellar remnant, whether a neutron star or black hole, will have had 40 million years to cool, spin down, and potentially merge with other objects. We're always studying stellar corpses, never witnessing stellar deaths in real time. The local group of galaxies, which includes the Milky Way, Andromeda, and about 80 smaller galaxies, spans roughly 10 million light-years across. Even within our own galactic neighborhood, light takes millions of years to travel from one side to the other. If an alien civilization in Andromeda decided to send us a message using the most powerful laser imaginable, we wouldn't receive it for 2.5 million years. By the time we got their message and sent a reply, 5 million years would have passed, enough time for significant evolutionary changes on both worlds. The cosmic web's largest structures, called superclusters, can span hundreds of millions of light years. The Laniakea supercluster, which contains our local group, stretches 520 million light-years across and contains the mass of 100,000 billion suns. Light takes over 500 million years to cross this structure, longer than complex life has existed on Earth. Even traveling at the universe's speed limit, you couldn't cross our local supercluster in the time it took for life to evolve from simple cells to human consciousness. Galaxy formation itself reveals the inadequacy of light speed for cosmic communication. Computer simulations show that galaxies grow through mergers and accretion over billions of years, but coordinating these processes across cosmic distances requires gravitational signals that travel at light speed. A galaxy merger between objects separated by millions of light-years takes hundreds of millions of years to complete, partly because gravitational information can only propagate at light speed. The universe's architecture is limited by its own speed limit. The cosmic microwave background shows tiny temperature fluctuations that represent the seeds of all cosmic structure. These quantum fluctuations, stretched to cosmic scales by inflation, had to grow through gravitational attraction over billions of years to become the galaxies we see today. But gravity propagates at light speed, meaning that even the formation of cosmic structure is limited by this fundamental velocity. The universe couldn't organize itself any faster than light speed allows. Void regions in the cosmic web, vast empty spaces between galaxy filaments, can span hundreds of millions of light-years. The Boötes void, one of the largest known empty regions, is so vast that light takes 330 million years to cross it. If you were somehow transported to the center of this cosmic desert, the nearest galaxy would be so far away that its light would take longer to reach you than it took for complex life to evolve on Earth. You would be truly alone in a way that's almost impossible to comprehend. The concept of cosmic simultaneity becomes meaningless at these scales. Events that appear to happen at the same time from our perspective might actually be separated by millions or billions of years. A supernova in Andromeda and a gamma ray burst in a distant galaxy might appear simultaneous to us, but they could have actually occurred millions of years apart. Light speed doesn't just delay information, it scrambles our perception of cosmic causality. Fast radio bursts, mysterious millisecond flashes of radio waves arrive at Earth from galaxies billions of light-years away. These enigmatic signals carry enormous amounts of energy but last for just thousandths of a second. By the time we detect them, the events that created them happened billions of years ago, when the universe was much younger and very different from today. We're receiving cosmic text messages from a universe that no longer exists in the form we're observing. The Drake equation attempts to estimate the number of communicating civilizations in our galaxy, but it doesn't account for light speed delays in cosmic communication. Even if thousands of civilizations exist in the Milky Way, the time required for signals to travel between them makes meaningful communication nearly impossible. A civilization on the opposite side of our galaxy would need to wait 100,000 years for a reply to any message they sent us. Entire civilizations could rise and fall in the time it takes for a single conversation. Gravitational lensing, where massive objects bend light from more distant sources, creates cosmic telescopes that allow us to see farther into the universe than would otherwise be possible. But even these natural magnifying glasses can't overcome light speed delays. The most distant galaxies observed through gravitational lensing appear as they were over 13 billion years ago when the universe was just a fraction of its current age. We're using cosmic optics to see deeper into the past, not to observe the present. The search for exoplanets has revealed thousands of worlds orbiting distant stars, but our knowledge of these planets is always years or decades out of date. The light from Kepler 452b, often called Earth's cousin, takes 1,400 years to reach us. Any signs of life or civilization on that world would be medieval by the time we detected them. We're searching for life in the cosmic past, never in the cosmic present. Stellar nurseries, regions where new stars are born from collapsing gas clouds, can span hundreds of light years and take millions of years to form new stellar systems. But even within these relatively compact regions, light speed delays mean that different parts of the nursery can't coordinate their star formation in real time. Changes in one region take hundreds of years to influence neighboring areas, making stellar birth a slow, uncoordinated process limited by the speed of information transfer. The galactic habitable zone, the region around the galaxy center where conditions might be suitable for life, spans thousands of light years. But even within this cosmic sweet spot, civilizations would be separated by distances that make communication extremely difficult. A message sent from one side of the habitable zone to the other would take thousands of years to arrive, making any form of galactic civilization or cooperation nearly impossible to maintain. Cosmic inflation theory suggests that the observable universe is just a tiny fraction of the total universe created during the Big Bang. If inflation is correct, then the vast majority of cosmic reality lies forever beyond our light horizon, unreachable no matter how long we wait. Light speed doesn't just limit our current view of the universe, it might permanently hide most of cosmic reality from our observation. The concept of cosmic evolution becomes frustrating when viewed through the lens of light speed limitations. We can observe galaxies at different stages of development by looking at different distances, but we can never watch a single galaxy evolve in real time. The universe is like a vast museum where we can see exhibits from different eras, but we can never witness the actual historical processes that created them. The Fermi paradox becomes even more puzzling when we factor in light speed limitations. If intelligent civilizations are common in the galaxy, why haven't we detected their signals? Part of the answer might be that we're looking for evidence of civilizations that existed millions of years ago, not civilizations that exist now. A thriving galactic empire could be flourishing on the other side of the Milky Way right now, but their radio signals wouldn't reach us for 50,000 years. We might be surrounded by cosmic chatter that simply hasn't had time to arrive. The concept of a galactic internet becomes laughably impractical when constrained by light speed. Imagine trying to browse websites hosted on servers orbiting stars thousands of light years away. Clicking a link would require waiting millennia for the page to load. Sending an email to someone in the galactic core would take 26,000 years for delivery and another 26,000 years to receive a reply. The universe's communication infrastructure is fundamentally broken by its own speed limit. Magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, occasionally release bursts of energy so powerful they can affect our planet's atmosphere from thousands of light years away. But these cosmic lighthouses are so distant that their most dramatic outbursts happened long before humans existed. We're experiencing the aftershocks of stellar catastrophes that occurred when Earth was still a molten ball of rock. Even the universe's most violent events are reduced to ancient history by the time their effects reach us. The cosmic distance ladder, the series of measurement techniques astronomers use to determine distances to far-off objects, relies entirely on light that has been traveling for vast periods. Cepheid variable stars, which pulsate with predictable periods, serve as cosmic standard candles for measuring distances up to hundreds of millions of light years. but the light we use to measure these stellar heartbeats left its source when complex life was just beginning to emerge from Earth's oceans. We're using ancient light to map a universe that has continued evolving long after that light began its journey. Dark energy surveys attempt to understand the mysterious force accelerating cosmic expansion by observing billions of galaxies across cosmic time. But these surveys face the fundamental limitation that they can only observe the past, never the present. The dark energy we measure in distant galaxies reflects conditions that existed billions of years ago. If dark energy is evolving or changing, we won't know about it until billions of years after the changes occur. We're trying to understand a dynamic universe using information that's always billions of years out of date. The concept of cosmic archaeology takes on new meaning when we realize that all astronomy is essentially the study of ancient artifacts. Every photon hitting our telescopes is a messenger from the past, carrying information about cosmic conditions that no longer exist. We're not observing the universe, we're excavating its history, one ancient light ray at a time. The cosmos is a vast archaeological site where the artifacts are scattered across billions of years of light travel time. Stellar streams, the tidal debris left behind when small galaxies are torn apart by larger ones, can stretch across hundreds of thousands of light years. These cosmic breadcrumb trails tell the story of galactic cannibalism, but the light showing us these disrupted galaxies began its journey hundreds of thousands of years ago. The galaxies we see being destroyed might have already been completely consumed, their stars redistributed throughout their captors. We're watching cosmic violence that concluded long before humans developed agriculture. The local void, a region of space near our galaxy that contains unusually few galaxies, spans about 150 million light-years across. This cosmic desert appears nearly empty from our perspective, but we're seeing it as it existed 150 million years ago when dinosaurs ruled the Earth. New galaxies might have formed in this region since then, or existing galaxies might have moved into the area, but we won't know about these changes for millions of generations. Cosmic ray particles accelerated to nearly light speed by supernova shockwaves and other extreme events take years or decades to reach Earth from their sources in distant parts of the galaxy. These subatomic messengers carry information about the most energetic processes in the cosmos, but by the time they arrive, the cosmic accelerators that created them might have already shut down or moved to completely different locations. We're studying particle physics experiments that were conducted in the cosmic past. The concept of nowness becomes completely meaningless at cosmic scales. There is no universal present moment that applies throughout the galaxy, let alone the universe. When we say that a star is exploding now in Andromeda, we mean that we're currently receiving light from an explosion that actually happened 2.5 million years ago. The universe doesn't have a synchronized timeline. It has billions of local timelines that intersect only through the delayed arrival of light signals. Galaxy rotation curves, which reveal the existence of dark matter, show us how galaxies were spinning millions of years ago, not how they're spinning now. The outer regions of large galaxies can extend for hundreds of thousands of light years, meaning that light from the galaxy's edge takes hundreds of thousands of years to reach the center. Even within a single galaxy, different regions exist in different time zones, making it impossible to observe the galaxy as a coherent, simultaneous system. The cosmic web's evolution happens so slowly that even light speed is barely adequate to carry information about structural changes. Galaxy filaments grow and merge over hundreds of millions of years, but the gravitational signals coordinating these processes travel at light speed. This means that changes in one part of a cosmic filament take millions of years to influence distant parts of the same structure. The universe's largest architectural projects are limited by the speed of their own blueprints. Supermassive black holes at galaxy centers can influence star formation throughout their host galaxies, but these effects propagate outward at light speed. When a central black hole becomes active and starts blowing powerful winds, it takes hundreds of thousands of years for these effects to reach the galaxy's outer regions. Galaxies can't respond to changes in their central engines in real time. They're always reacting to ancient history. The concept of cosmic weather becomes absurd when constrained by light speed. Imagine trying to predict cosmic storms when your weather data is always millions or billions of years out of date. We observe galaxy collisions, stellar explosions, and black hole outbursts, but we're seeing cosmic weather patterns from the deep past. The current state of cosmic weather remains completely unknown, hidden behind the light speed barrier. Gravitational wave astronomy has opened a new window on the universe, but gravitational waves travel at exactly light speed, facing the same temporal limitations as electromagnetic radiation. When we detect waves from colliding black holes billions of light-years away, we're experiencing gravitational tremors from cosmic earthquakes that happened billions of years ago. The universe's most exotic phenomena are still trapped behind the same frustratingly slow speed limit. The search for techno-signatures, evidence of advanced alien civilizations, faces the cruel reality that any signals we detect will be ancient by the time they reach us. A civilization that built a Dyson sphere around their star 1,000 years ago would appear to us as they were 1,000 years ago, not as they are now. We might detect evidence of civilizations that have already transcended physical existence or gone extinct, while missing civilizations that are thriving in the cosmic present. Cosmic inflation theory suggests that during the universe's first fraction of a second, space expanded faster than light by enormous factors. This brief period of faster-than-light expansion created the cosmic horizon that limits our view today. Ironically, the only time in cosmic history when information could travel faster than light was during the universe's birth, before light itself existed. Since then, the cosmos has been trapped by its own speed limit. The observable universe represents just a tiny fraction of the total universe, if space is infinite, or even just much larger than we can see. Light speed doesn't just limit our current view, it might permanently hide most of cosmic reality from our observation. We're like deep-sea creatures living near a thermal vent, able to see only a tiny bubble of illuminated water, while vast oceans of darkness stretch beyond our perception. The concept of cosmic simultaneity breaks down completely when we consider relativistic effects at galactic scales. Einstein's theory of relativity tells us that there is no universal now. Simultaneity depends on your reference frame and motion through space. For observers moving at different velocities relative to distant galaxies, events that appear simultaneous can actually be separated by thousands or millions of years. The universe doesn't just lack a universal clock, it lacks the very concept of universal time. Stellar archaeology, the study of ancient stars to understand early cosmic conditions, faces the fundamental limitation that we can only observe these stellar fossils as they appeared in the distant past. The oldest stars in our galaxy, formed when the universe was just a few billion years old, appear to us as they were millions of years ago. These stellar time capsules carry information about primordial conditions, but their current state, if they even still exist, remains completely unknown. The Milky Way's spiral arms, those beautiful curved structures that give our galaxy its distinctive appearance, rotate around the galactic center like a cosmic pinwheel. But these spiral patterns are density waves that propagate through the galaxy at speeds much slower than light. It takes millions of years for spiral wave patterns to travel from the galactic center to the outer regions, meaning that different parts of our galaxy exist in different phases of the spiral pattern. We can't even see our own galaxy's current structure in real time. Cosmic voids, those vast empty regions between galaxy filaments, present their own light speed challenges. The largest known void, the Bootes supervoid, is so enormous that if you were placed at its center, the nearest galaxy would be so far away that its light would take 330 million years to reach you. You would experience a level of cosmic isolation that's almost impossible to comprehend, surrounded by darkness so complete that the nearest source of light is farther away than the time it took for complex life to evolve on Earth. The concept of galactic archaeology becomes even more complex when we realize that galaxy mergers and interactions happen over hundreds of millions of years. When we observe the antennae galaxies, two spiral galaxies in the process of merging, we're seeing a cosmic collision that began hundreds of millions of years ago and won't be complete for hundreds of millions of years in the future. We're witnessing a single frame from a cosmic movie that plays out over timescales that dwarf human comprehension. Quasar variability studies reveal that these cosmic powerhouses can change brightness dramatically over periods of months or years. But for the most distant quasars observed when the universe was less than 1 billion years old, we're seeing variability that occurred over 12 billion years ago. These ancient light curves tell us about black hole feeding patterns from when the universe was young and chaotic, but the current state of these objects, if they even still exist as quasars, remains completely mysterious. The cosmic distance scale becomes a temporal scale when viewed through the lens of light speed limitations. Astronomers measure distances in light years, but they're really measuring time delays. When we say a galaxy is 1 billion light years away, we're saying that we're seeing it as it existed 1 billion years ago. Distance and time become interchangeable, creating a universe where space and history are inextricably linked. Planetary nebulae, the beautiful shells of gas expelled by dying stars, can expand for thousands of years before fading away. But even these relatively nearby objects located within our own galaxy appear to us as they were years or decades ago. The intricate structures we observe in nebulae like the Ring Nebula or the Cat's Eye Nebula are ancient light sculptures frozen in time by the delay between emission and observation. We're seeing stellar death throes that concluded before our grandparents were born. The search for biosignatures in exoplanet atmospheres faces the sobering reality that any signs of life we detect will be ancient by the time they reach us. If we discovered oxygen in the atmosphere of Proxima Centauri b, indicating possible photosynthesis, that oxygen signature would be over 4 years old by the time we detected it. The life that produced it might have already gone extinct or evolved into something completely different. We're searching for life in the cosmic past, never in the cosmic present. Cosmic ray astronomy studies the highest energy particles in the universe, but these subatomic messengers face the same light speed limitations as photons. Ultra-high energy cosmic rays carrying energies equivalent to a baseball traveling at 60 miles per hour, concentrated in a single proton, take years or decades to reach Earth from their sources in distant galaxies. By the time we detect these cosmic bullets, the particle accelerators that created them, supernova remnants, black hole jets, or exotic objects we haven't yet discovered, might have already shut down or moved to completely different locations. The concept of cosmic evolution becomes frustrating when constrained by light speed delays. We can observe galaxies at different stages of development by looking at different distances, creating a cosmic timeline that spans billions of years. But we can never watch a single galaxy evolve in real time. It's like trying to understand human development by looking at photographs of different people at different ages, rather than watching one person grow up. We see cosmic evolution as a series of snapshots, never as a continuous process. Stellar formation regions where new stars are born from collapsing gas clouds can span hundreds of light years and take millions of years to complete their stellar nursery duties. But even within these relatively compact regions, light speed delays mean that different parts of the star-forming region can't coordinate their activities in real time. Changes in one part of a stellar nursery take hundreds of years to influence neighboring regions, making star formation a slow, uncoordinated process, limited by the speed of information transfer. The galactic halo, a roughly spherical region surrounding our galaxy that contains dark matter and ancient stars, extends for hundreds of thousands of light years. Objects in the outer halo appear to us as they were hundreds of thousands of years ago, when early humans were just beginning to develop language and culture. The most distant parts of our own galaxy are so far away that their light began its journey before human civilization existed. Gravitational microlensing events, where the gravity of a foreground object magnifies light from a more distant source, can reveal planets orbiting stars thousands of light years away. But these cosmic alignments show us planetary systems as they existed thousands of years ago, not as they are today. We might be detecting planets that have already been destroyed by stellar evolution, or missing planets that have formed since the light we're observing began its journey. The cosmic web's largest structures, superclusters containing thousands of galaxies, span hundreds of millions of light years. The Laniakea supercluster, which contains our local group, is so vast that light takes over 500 million years to cross it. This means that galaxies on opposite sides of our supercluster exist in completely different cosmic epochs from our perspective. We're not observing a coherent structure, we're seeing a collection of galaxies frozen at different moments in cosmic history. Fast radio bursts, those mysterious millisecond flashes of radio energy, arrive at Earth from galaxies billions of light years away. These enigmatic signals carry enormous amounts of energy but last for just thousandths of a second. The events that created them, possibly magnetar flares, black hole mergers, or exotic physics we don't yet understand, happened billions of years ago when the universe was much younger and very different from today. We're receiving cosmic telegrams from a universe that no longer exists in the form we're observing. The concept of cosmic archaeology takes on profound meaning when we realize that every astronomical observation is essentially the excavation of ancient light. Telescopes are time machines that allow us to dig through layers of cosmic history, but we can never reach the present. The deeper we look into space, the further back in time we see, creating a universe where the most distant objects are also the most ancient. We're cosmic paleontologists studying fossils made of light. Stellar streams, the tidal debris left behind when small galaxies are disrupted by larger ones, can stretch across hundreds of thousands of light years. These cosmic breadcrumb trails tell stories of galactic cannibalism, but the light showing us these stellar streams began its journey hundreds of thousands of years ago. The disruption events we observe might have already concluded, with the victim galaxies completely absorbed by their captors. We're watching cosmic violence that ended long before human civilization began. The concept of cosmic weather forecasting becomes absurd when we consider light speed delays. Imagine trying to predict solar storms when your data about the sun's surface is already 8 minutes old by the time it reaches Earth. Now scale that up to galactic proportions. Predicting cosmic weather patterns when your observational data is millions or billions of years out of date. We observe massive stellar explosions, galaxy collisions, and black hole outbursts, but we're seeing cosmic weather from the deep past, while the current cosmic climate remains completely hidden from our view. Type Ia supernovae, the stellar explosions that serve as cosmic standard candles for measuring distances and cosmic expansion, face their own light speed limitations. These thermonuclear detonations of white dwarf stars can be seen from billions of light years away, but by the time we detect them, the explosions happened billions of years ago. The stellar remnants, whether neutron stars, black holes, or completely dispersed matter, have had billions of years to cool, evolve, and potentially merge with other objects. We're studying stellar death certificates that were written in the cosmic past. The Hubble Space Telescope's deep field observations reveal galaxies that existed when the universe was just a few 100 million years old. These primordial galaxies appear small, chaotic, and actively forming stars at prodigious rates. But their current state after over 13 billion years of evolution remains completely unknown. They might have grown into massive elliptical galaxies, merged with other systems, or been torn apart by tidal forces. We're seeing cosmic baby pictures while the subjects have aged into cosmic senior citizens. Pulsar timing arrays, networks of precisely monitored neutron stars that act as cosmic clocks, have recently detected the gravitational wave background, a constant rumble of space-time distortions from countless black hole mergers throughout cosmic history. But even these gravitational waves travel at light speed, meaning we're detecting the accumulated gravitational noise from black hole collisions that happened millions and billions of years ago. The current state of cosmic gravitational activity remains hidden behind the light speed barrier. The concept of galactic rotation becomes complex when we consider that different parts of a galaxy exist in different time zones from our perspective. The Milky Way's outer regions where we're located appear to us as they were thousands of years ago due to light travel time within our own galaxy. The galactic center appears as it was 26,000 years ago, when humans were still hunter-gatherers. We can't even observe our own galaxy as a coherent, simultaneous system. It's a collection of regions frozen at different moments in galactic history. Cosmic void evolution presents another example of light speed's inadequacy for understanding cosmic processes. These vast empty regions between galaxy filaments grow over hundreds of millions of years as galaxies are pulled toward denser regions by gravity. But the light showing us void boundaries began its journey hundreds of millions of years ago when the cosmic web had a very different structure. Voids that appear empty to us might have been filled with galaxies since the light we're observing began its journey, or new voids might have formed that we won't see for hundreds of millions of years. The search for intermediate mass black holes, objects with masses between stellar mass and supermassive black holes, faces the challenge that these elusive objects might be hidden by light speed delays. If such black holes exist in globular clusters or dwarf galaxies, we're seeing these systems as they appeared thousands or millions of years ago. The black holes we're searching for might have already grown into supermassive objects, merged with other black holes, or been ejected from their host systems through gravitational interactions. Stellar kinematics, the study of how stars move through galaxies, reveals the gravitational influence of dark matter and the history of galactic formation. But stellar motions change over millions of years, and the light showing us current stellar positions is already years or decades old by the time it reaches us. We're trying to understand galactic dynamics using position data that's constantly becoming more outdated. It's like trying to predict traffic patterns using photographs that were taken years ago. The cosmic distance ladder relies on a series of overlapping measurement techniques, each calibrated using objects at different distances and therefore different look-back times. Cepheid variable stars, used to measure distances up to hundreds of millions of light-years, appear to us as they were millions of years ago. Type Ia supernovae, used for even greater distances, show us cosmic expansion as it was billions of years ago. We're building a distance scale using rulers that exist at different moments in cosmic history. Galaxy cluster dynamics reveal the presence of dark matter through gravitational lensing and X-ray observations of hot gas. But these massive systems, containing thousands of galaxies spread across millions of light-years, can't be observed as coherent structures due to light-speed delays. Different parts of a galaxy cluster exist in different time zones from our perspective, making it impossible to study cluster dynamics in real time. We're trying to understand gravitational choreography using dancers frozen at different moments in their performance. The concept of cosmic simultaneity becomes even more problematic when we consider that the universe is expanding. Not only are we seeing distant objects as they were in the past, but the space between us and those objects has been stretching during the light travel time. A galaxy that appears to be 10 billion light-years away actually emitted its light when it was much closer to us, and it's now much farther away due to cosmic expansion. We're seeing objects that no longer exist where we observe them to be. Magnetospheric physics around other stars faces the limitation that stellar magnetic fields can change dramatically over periods of years or decades. The magnetic activity we observe on distant stars reflects conditions that existed years ago, not current magnetic field configurations. Stellar flares, coronal mass ejections, and magnetic reconnection events that we detect are ancient history by the time their light reaches our telescopes. We're studying stellar magnetic weather from the past while current conditions remain unknown. The search for gravitational wave sources using electromagnetic follow-up observations faces timing challenges created by light speed delays. When gravitational wave detectors like LIGO identify a black hole merger, the electromagnetic counterpart, if it exists, must be observed quickly before it fades. But the light from these events has been traveling for millions or billions of years, meaning we're trying to catch the afterglow of explosions that happened in the cosmic past. We're cosmic crime scene investigators arriving billions of years after the incident. Exoplanet atmospheric studies using transit spectroscopy reveal the chemical composition of alien atmospheres, but these observations show us atmospheric conditions as they existed years or decades ago when the light left the planet's star. Atmospheric chemistry can change rapidly due to geological activity, impacts, or biological processes. We might be detecting oxygen signatures from photosynthesis that ended years ago, or missing atmospheric changes that occurred after the light we're observing began its journey. The concept of cosmic archaeology extends to the study of ancient light itself. The cosmic microwave background radiation, the afterglow of the Big Bang, has been traveling for 13.8 billion years. This ancient light carries information about the universe when it was only 380,000 years old, but it tells us nothing about cosmic conditions in the intervening billions of years. We have a baby picture of the universe and recent photographs, but the entire middle age of cosmic history remains hidden. Stellar population synthesis, the study of how stellar populations evolve over time, faces the challenge that we can only observe stellar populations as they appeared in the past. Globular clusters containing some of the oldest stars in the galaxy appear to us as they were thousands of years ago. The current state of these ancient stellar systems, whether they've lost stars to tidal stripping, experienced stellar collisions, or undergone other evolutionary changes, remains unknown until their light catches up with us. The study of cosmic chemical evolution relies on observations of gas clouds and stellar atmospheres at different distances and therefore different cosmic epochs. We can trace how the universe's chemical composition has changed over time by looking at objects at different distances, but we can never observe chemical evolution happening in real time. It's like trying to understand how a recipe changes by looking at ingredients from different time periods, rather than watching the cooking process unfold. Cosmic ray propagation through the galaxy faces its own light speed limitations. These high-energy particles, accelerated by supernova shockwaves and other extreme events, take thousands of years to travel from their sources to Earth. The cosmic ray particles hitting our atmosphere right now were accelerated by stellar explosions that happened millennia ago. We're studying particle physics experiments that were conducted in the cosmic past, with no knowledge of current cosmic ray production rates. The concept of galactic chemical gradients, where the abundance of heavy elements changes with distance from the galactic center, becomes complicated by light speed delays. Different parts of the galaxy appear to us at different epochs, making it difficult to study current chemical distributions. The metallicity gradients we observe reflect conditions that existed at different times in galactic history, not a coherent snapshot of current galactic chemistry. The phenomenon of cosmic time dilation adds another layer of complexity to our understanding of light speed's inadequacy. As the universe expands, time itself runs differently at different cosmic epochs. Clocks in the early universe, when matter was denser and space was more curved, ticked at different rates compared to today. This means that not only are we seeing distant objects as they were in the past, but we're seeing them operating under different temporal conditions. A process that took 1 billion years in the early universe might take longer today due to the changing rate of cosmic time itself. Stellar nurseries, where new stars are born from collapsing molecular clouds, present fascinating examples of light speed's limitations on our understanding of cosmic processes. The Eagle Nebula's famous pillars of creation, those towering columns of gas and dust where stars are forming, appear to us as they were 7,000 years ago. Recent infrared observations suggest that these pillars might have already been destroyed by a nearby supernova explosion, but the light showing their destruction won't reach us for another 1,000 years. We might be admiring cosmic sculptures that no longer exist. The concept of galactic cannibalism, where larger galaxies consume smaller ones, unfolds over hundreds of millions of years. When we observe the Sagittarius dwarf galaxy being torn apart by the Milky Way's gravity, we're seeing a cosmic meal that began millions of years ago and won't be completed for millions of years in the future. The tidal streams of stars being stripped from the dwarf galaxy appear to us as they were at different points in this slow-motion destruction, creating a time-lapse movie played out across the sky. Cosmic web filaments, those vast highways of dark matter connecting galaxy clusters, evolve on timescales that make light speed seem glacial. These structures, spanning hundreds of millions of light-years, grow and change over billions of years, but the light showing us their current configuration left different parts of these filaments at different times, creating a patchwork view of cosmic architecture that spans billions of years of structural evolution. We're seeing cosmic construction projects at different stages of completion. The study of active galactic nuclei powered by supermassive black holes consuming matter faces the challenge that these objects can change dramatically over periods of years or decades. A quasar that appears bright and active to us might have already shut down years ago when its central black hole exhausted its fuel supply. Conversely, dormant galaxies might have recently become active, but we won't see their awakening until years or decades after it occurs. We're studying cosmic powerhouses that exist in a state of temporal uncertainty. Gravitational wave astronomy has opened a new window on the universe, but these ripples in space-time face the same light speed limitations as electromagnetic radiation. When LIGO detected gravitational waves from neutron stars colliding 130 million light-years away, we experienced space-time tremors from a cosmic earthquake that happened when dinosaurs roamed the Earth. The neutron star remnant, whether it formed a black hole or a more massive neutron star, has had 130 million years to evolve since the collision we detected. The concept of cosmic variance becomes more complex when we consider that different regions of the universe exist at different cosmic times from our perspective. Statistical studies of galaxy properties must account for the fact that nearby galaxies appear as they were recently, while distant galaxies appear as they were billions of years ago. We're trying to understand cosmic statistics using a sample that spans billions of years of cosmic evolution, like trying to understand human demographics using census data from different centuries. Stellar evolution models predict how stars change over millions or billions of years, but we can only test these models by observing stars as they appeared in the past. A massive star that we observe today might have already exploded as a supernova, but we won't see the explosion until years or decades after it occurs. We're testing theories about stellar death using observations of stars that might already be stellar corpses. Our understanding of stellar evolution is always playing catch-up with stellar reality. The search for dark matter signatures faces the challenge that any evidence we detect reflects conditions in the cosmic past. If dark matter particles interact with ordinary matter in ways that produce detectable signals, those signals from distant sources are already years or decades old by the time they reach our detectors. We might be searching for evidence of dark matter interactions that no longer occur, or missing new types of interactions that have developed since the light we're observing began its journey. Cosmic ray astronomy studies reveal the most energetic processes in the universe, but these subatomic messengers carry information about cosmic conditions from years or decades in the past. Ultra-high-energy cosmic rays, with energies that shouldn't be possible according to our understanding of cosmic acceleration mechanisms, tell us about particle physics experiments that were conducted in distant galaxies long ago. The cosmic accelerators that created these particles might have already shut down or evolved into something completely different. The concept of cosmic noon, the epoch about 10 billion years ago when star formation peaked throughout the universe, can only be studied by observing galaxies at enormous distances. We see this cosmic golden age by looking at galaxies billions of light-years away, but their current state remains completely unknown. These galaxies have had billions of years to evolve since cosmic noon, potentially transforming into completely different types of objects. We're studying the universe's most productive era using ancient light from galaxies that might no longer exist. Planetary system formation around other stars faces similar temporal challenges. When we observe protoplanetary disks around young stars, we're seeing planet formation as it occurred years or decades ago. The planets that might be forming in these disks could have already completed their formation, been ejected from their systems, or failed to form at all. We're studying planetary birth using baby pictures that might not reflect current planetary nursery conditions. The study of cosmic magnetic fields relies on observations of synchrotron radiation from charged particles spiraling around magnetic field lines. But these observations show us magnetic field configurations as they existed when the light left its source, not current magnetic field structures. Cosmic magnetic fields can change over thousands or millions of years due to stellar winds, supernova explosions, and galactic rotation. We're mapping magnetic field fossils, not current magnetic field geography. Supernova remnants, the expanding shells of gas and debris left behind by stellar explosions, evolve over thousands of years as they interact with the surrounding interstellar medium. But even these relatively nearby objects appear to us as they were years or decades ago. The shock waves, particle acceleration, and chemical enrichment we observe in supernova remnants reflect processes that concluded before our observations began. We're studying stellar explosion aftermaths that have continued evolving since the light showing them to us began its journey. The concept of galactic archaeology, using the chemical compositions and motions of stars to understand galactic formation history, faces the limitation that stellar properties can change over millions of years. The stars we observe today might have different chemical abundances, orbital motions, or even stellar companions than they had when the light we're detecting left them. We're trying to reconstruct galactic history using evidence that's constantly becoming more outdated. Cosmic void studies reveal vast empty regions between galaxy filaments, but these voids evolve over hundreds of millions of years as galaxies move under gravitational influence. The void boundaries we observe reflect galaxy positions from hundreds of millions of years ago, not current void structures. New galaxies might have moved into apparently empty regions, or existing galaxies might have been pulled out of voids by gravitational attraction. We're mapping cosmic emptiness that might no longer be empty. The search for intermediate mass black holes, objects with masses between stellar mass and supermassive black holes, faces the challenge that these elusive objects might be hidden by evolutionary changes that occurred after the light we're observing began its journey. A stellar mass black hole observed years ago might have grown into an intermediate mass object through accretion or mergers, while intermediate mass black holes might have grown into supermassive objects or been ejected from their host systems. Stellar cluster dynamics, the study of how stars move within globular clusters and open clusters, must account for the fact that stellar motions change over thousands or millions of years. The cluster configurations we observe reflect stellar positions from when the light left the cluster, not current stellar arrangements. Stars might have been ejected from clusters, new stars might have been captured, or entire clusters might have been disrupted by tidal forces since the light we're observing began its journey. The concept of cosmic evolution becomes a study of cosmic history rather than cosmic process when constrained by light speed limitations. We can observe the universe at different epochs by looking at different distances, but we can never watch cosmic evolution happening in real time. It's like trying to understand biological evolution by looking at fossils from different time periods rather than observing living organisms adapt and change. We see the results of cosmic evolution, never the process itself. The phenomenon of redshift, where light from distant objects is stretched to longer wavelengths by cosmic expansion, creates an additional layer of temporal confusion. Not only are we seeing distant galaxies as they were billions of years ago, but their light has been stretched and distorted during its journey through expanding space. The colors we observe don't represent the actual colors these galaxies emitted. They're shifted versions that have been modified by billions of years of cosmic expansion. We're seeing the universe through a temporal filter that distorts both time and appearance. Binary star systems, where two stars orbit around their common center of mass, present fascinating examples of light speed's impact on astronomical observations. The orbital periods of these stellar dances can range from hours to thousands of years, but we observe their gravitational ballet as it occurred when the light left the system. For distant binary stars, we might be watching orbital phases that completed years or decades ago. The stars might have already merged, exploded, or been disrupted by passing objects, but we continue to see their ancient dance frozen in time. The concept of stellar archaeology becomes even more complex when we consider that the oldest stars in our galaxy appear to us as they were thousands of years ago. These ancient stellar fossils, formed when the universe was just a few billion years old, carry information about primordial conditions in their atmospheric compositions. But their current state, whether they've evolved into white dwarfs, exploded as supernovae, or been stripped of their outer layers, remains unknown until their light catches up with our observations. Cosmic string theory, if these hypothetical one-dimensional defects in space-time exist, would create observable effects that propagate at light speed. These cosmic strings left over from phase transitions in the early universe could stretch across billions of light years and create distinctive signatures in the cosmic microwave background. But any evidence we might detect would show us cosmic string configurations from the early universe, not their current state after billions of years of cosmic evolution. The study of galactic winds, massive outflows of gas driven by stellar feedback and black hole activity, faces the challenge that these phenomena can change rapidly over astronomical timescales. A galaxy that appears to be driving a powerful wind might have already exhausted its gas supply and shut down the outflow. Conversely, galaxies that appear quiescent might have recently begun driving winds that we won't observe until the light showing these changes reaches us years or decades from now. Planetary nebulae, those beautiful shells of ionized gas expelled by dying stars, evolve over thousands of years as they expand into the surrounding interstellar medium. But even these relatively nearby objects located within our own galaxy appear to us as they were years or decades ago. The intricate structures we observe, the rings, jets, and knots of glowing gas, might have already dispersed or evolved into completely different configurations. We're admiring cosmic art galleries displaying works that might no longer exist. The concept of cosmic chemical evolution relies on observations of gas clouds and stellar atmospheres at different distances, and therefore different cosmic epochs. We can trace how the universe's chemical composition has changed over time by looking at objects at different distances, but this creates a fundamental problem. We're trying to understand a dynamic process using static snapshots from different eras. It's like trying to understand how a city develops by looking at photographs taken at different times, rather than watching the construction process unfold. Gravitational microlensing events, where the gravity of a foreground object magnifies light from a more distant source, can reveal planets orbiting stars thousands of light years away. But these cosmic alignments show us planetary systems as they existed thousands of years ago, not as they are today. The planets we detect might have already been destroyed by stellar evolution, migrated to different orbits, or been ejected from their systems entirely. We're discovering ancient planetary systems while their current configurations remain completely unknown. The search for biosignatures in exoplanet atmospheres faces the sobering reality that any signs of life we detect will be ancient by the time they reach us. Atmospheric oxygen produced by photosynthesis could indicate the presence of life on distant worlds. But the oxygen signatures we might detect from planets hundreds of light years away would reflect biological activity that occurred centuries ago. The life that produced these signatures might have already evolved into something unrecognizable, gone extinct, or developed technology that completely altered their planet's atmospheric composition. Cosmic ray propagation through the galaxy creates its own temporal puzzles. These high-energy particles, accelerated by supernova shockwaves and other extreme events, take thousands of years to travel from their sources to Earth. The cosmic ray particles hitting our atmosphere right now carry information about stellar explosions that happened millennia ago. We're studying the aftermath of cosmic violence that occurred when human civilization was just beginning to develop agriculture and writing. The concept of galactic habitable zones, regions around galaxy centers where conditions might be suitable for life, must account for the fact that these zones change over billions of years as galaxies evolve. The habitable zone we observe in distant galaxies reflects conditions that existed billions of years ago, not current habitability. Stellar formation rates, supernova frequencies, and radiation environments have all changed since the light we're observing began its journey. We're mapping ancient habitability, not current prospects for life. Stellar stream archaeology, the study of tidal debris from disrupted satellite galaxies, reveals the merger history of large galaxies like the Milky Way. But these stellar streams appear to us as they were thousands or millions of years ago, depending on their distance. The disruption events we observe might have already concluded, with the satellite galaxies completely absorbed and their stellar streams dispersed throughout the host galaxy. We're studying galactic cannibalism using evidence that's constantly becoming more outdated. The phenomenon of cosmic variance, where different regions of the universe show different statistical properties, becomes more complex when we consider temporal effects. Large-scale structure surveys must account for the fact that nearby regions appear as they were recently, while distant regions appear as they were billions of years ago. We're trying to understand cosmic statistics using a sample that spans billions of years of cosmic evolution, like trying to understand population demographics using census data from different millennia. Vast radio bursts, those mysterious millisecond flashes of radio energy, arrive at Earth from galaxies billions of light-years away, carrying enormous amounts of energy in incredibly brief pulses. But these enigmatic signals represent events that occurred billions of years ago when the universe was much younger and potentially very different from today. The sources of these bursts, whether magnetars, black hole mergers, or exotic physics we don't yet understand, might have evolved into completely different objects or ceased to exist entirely. The study of cosmic reionization, the epoch when the first stars and galaxies ionized the neutral hydrogen that filled the early universe, can only be observed by looking at the most distant objects we can detect. We see this cosmic phase transition by observing galaxies and quasars from when the universe was less than 1 billion years old. But these observations show us reionization as it occurred over 13 billion years ago, not as a process we can study in real time. We're investigating one of the most important transitions in cosmic history using ancient light from objects that might no longer exist. Supermassive black hole growth, the process by which these cosmic monsters accumulate mass over billions of years, can only be studied by observing black holes at different distances and therefore different cosmic epochs. We see supermassive black holes at various stages of their growth by looking at quasars and active galactic nuclei at different redshifts. But this creates a fundamental limitation. We can never watch a single black hole grow over time. We're studying black hole evolution using snapshots from different eras, like trying to understand human development by looking at photographs of different people at different ages. The concept of cosmic dawn, the epoch when the first stars formed and began to illuminate the universe, represents the earliest period we can potentially observe with electromagnetic radiation. But even our most powerful telescopes can only show us cosmic dawn as it occurred over 13 billion years ago. The first stars, if any still exist, have had over 13 billion years to evolve, merge, or explode. We're studying the universe's birth using baby pictures while the universe has aged into cosmic maturity. Galactic merger simulations predict how galaxies interact and combine over hundreds of millions of years, but we can only test these models by observing galaxy mergers as they appeared in the past. The antennae galaxies, two spiral galaxies in the process of merging, appear to us as they were 65 million years ago, when dinosaurs were going extinct on Earth. The current state of this cosmic collision, whether the galaxies have completed their merger or are still in the process of combining, remains unknown until their light catches up with our observations. The search for dark energy signatures relies on observations of distant supernovae and galaxy clusters, but these observations show us dark energy's effects as they occurred billions of years ago, not its current influence on cosmic expansion. If dark energy is evolving or changing over time, we won't know about these changes until billions of years after they occur. We're trying to understand a potentially dynamic force using information that's always billions of years out of date. If this cosmic perspective has blown your mind, hit that subscribe button and smash the like button. Your support means everything to me. And if you're hungry for more mind-bending revelations about our universe, check out this video at the left side of the screen where we explore what would happen if we traveled faster than the speed of light. See you there.